We're going to do Radix Sort here. I think we're recording. Let's check. I think we're good. We're counting. We're good. All right, so you lost that last algorithm. It was a really good one. All right, so now Radix Sort. Radix Sort is, when I was in high school, we had punch cards, right? And so imagine this being a punch card, and every column is only a digit between 0 and some k minus 1, and we only have a few digits, right? And we want to sort these cards, right? And so those are the cards we want to sort. And we have a machine, a big machine, and what the machine will do is if you put all the cards in the machine and you select a column, then it does what we call it sorts them based on that column. Right? Really what it does is it looks at each column and it does bucket sort, just like we were talking about. Right? It puts all the zeros here and all the ones here, and then you restack them up. But basically, it sorts the card based on that column. Everybody buy that? And another thing that's true about it, I think it's probably on the next slide, it's called the stable sort. And what stable sort means is if there are two cards with the same value, right, then it doesn't matter what order they go in. So don't change their order, right? It keeps the order in the same order if there's no reason to change the order. Everybody understand what the operation is? So you select a column, it sorts based on that column, keeping the cards in the same order if they have the same digit. All right, so now our goal is to sort. And you might ask, well, which digit do we sort with respect to first? You'd think, do we sort with respect to the high order digit, the middle digit, or the low order digit first? I got some highs, I got some lows. Highs and lows. Furthest right, that's lowest order. All right, so which first? Well, let's try the high order digit first. That seems like it would be a good goal, right? If we were humans, that's probably what we would do. We would sort with respect to the high order digit, and that's great. And then when we sort with respect to the second order digit, it messed them all up, right? That was not useful. If it was useful, what you would have to do is sort these guys with respect to the second digit and sort these. But then we have too many piles, right? So that doesn't work. And so, as people might have noticed, is, well, what we're going to do is we're going to sort in respect to the low order digit, right? And that seems like a weird thing to do because they're not in order whatsoever, right? But we did it. That was fun. And now we're going to sort with respect to the second order digit, right? And we get this. All right? Everybody see that? Here we started them in a random order. We sorted with respect to the first digit, and then we sorted with respect to the second digit, and that's what we get. All right? So now we're looking for a loop invariant. Anybody see what's true about this, which is great?
The first one is sorted the range. The range 2.
Right, 2. Right? We haven't looked at this data at all, right? So you can't expect anything's true about that data. So let's think about this as more of the input, right? Remember what more of the input is? I've looked at this much of the input, and if I considered that much of the input to be the entire input, then I have the answer. All right? So here what we're saying is, I've only looked at the first 2 digits. And if all that there was the first 2 digits, then I've got them sorted, right? Remember, I sorted with respect to the first digit, which meant it was sorted with respect to the first digit. And now, what we're claiming, and we haven't proved it yet, but proof by example, it feels like what we have is our loop invariant is that we've sorted them with respect to the first 2 digits, right? Everybody get that loop invariant? All right, so now what we want to prove is that we can maintain that. That's our loop invariant, that they're sorted with respect to the first I digits, right? And now we want to prove that we can maintain that, right? We're at the top of the loop. We know they're sorted with respect to the first I digits. And then what's our action? our action is to sort them with respect to the I plus first digit. And what do we want in the end? Is we want them sorted with respect to the first I plus 1 digits. Right? Everybody understand what we're trying to do? Right? You with me here? They're sorted here with respect to these 2 digits. Then we sort with respect to the third. And I want to prove to you that now they're sorted with respect to the first 3 digits. Right? Everybody good? All right. Proof. Right? So, in order to prove that these sorted with respect to the first I plus 1 digits, well, here I'm breaking it up into blocks based on the third digit. In order to prove they're sorted, what I'm going to do is I'm going to look at, it's sufficient to look at any 2 cards and prove that those cards are in the right order. Right? If I look at any 2 cards and show they're in the right order, then they're sorted. Right? So, case 1, is suppose that the cards, their first digits are different. Right? Then because I sorted in respect to these digits, they're in the right order. Right? Wouldn't you agree with that? So now there's a second case. Suppose they have the same first digit. Right? If they have the same first digit, let's come over here to wherever they are. They were sorted. By the loop invariant, they were sorted before, right? And because because these digits are the same and it's a stable sort, the stable sort doesn't change their order. Right? Does that make sense? Do people follow that? Yeah. So, that's the proof that radix sort works. Right? Everybody buy that? All right. We're going to do one more real quick. Counting sort. It's now we have our input is just a bunch of digits, but we don't have very many values, right? In this case, you see they only go up to 3, 0 through 3. But this 0 is not the same as this 0. This 0 contains a lot of data that's clinging along with it. So the output is going to be those numbers sorted, but it needs to be stable. These 2 zeros, they gotta stay in the same order, right? Everybody got the problem? Right? It's basically what we call the stable sort. We want to sort them. All right. So the algorithm is we're going to count. It's counting sort. We're going to count, and we're going to figure out where every number goes. All right? So, this is just saying that they're stable, right? These 2 are the same digit, so they got to go in the same order, right? That's the stable sort aspect. All right, so that number there. Look at that number there. Let's figure out where it goes by counting. All right? Anybody want to see where it goes? There's 1, 2, 3. One's before it. So 1, 2, 3. It's that one. Right? That's where it goes. And how do I know it goes there? Is I count how many things go before it. Right? And who goes before it? Well, all the zeros go before it. All cards, numbers that are smaller than it go before it. And then all numbers which are the same value that are before it go before it. Are you with me here? All right, so let's do that counting. Right, so it goes there, right? And we're going to index them. We're going to index them starting at 0. And why do we index starting at 0? The joyful thing of that is that, look at, there are 8 guys before it, and hence it goes in spot 8. Right? Here, there's 0 guys before this, so it goes 0, right? This guy, there's 1 person before it, so it goes in location 1. So if we know how many people go before it, we know where to put it. Right? So why are there 8 people before it? Well, because there are 5 numbers smaller than it, and there are 3 ones before it. Right? Everybody with me here? We're counting. All right. So we count these. So we start off, here's our various values, and what we want to count is how many zeros are there? 1, 2, 3, 4, 5. There are 5 zeros, right? And there are 9 ones, and there are 3 2s, right? We want to count them, right? So suppose you have n records with k different values. How long does it take to do all these counts? I could count the zeros. I could count the ones. How long does that take? N times k, right? So it could take n times k time. Does that make sense? Can we do it faster? How do you do it faster? And you increment. Yeah, dudes, no, we've got to do it faster. You go through once, right? You go through once, and the loop invariant that we're maintaining is that we know how many we've seen so far, right? And when you see a 2, you increment the 2's count. So that, right? All right, so that was good. And now, here's the counts, and now we want to compute something else. We want to compute how many records are there smaller than 0, right? Well, they're clearly 0 smaller than 0, right? How many are smaller than 1? Well, they're 5 smaller than 1. How many are smaller than 2? They're 14 smaller than. How many are smaller than 3? 17, right? Now, how long does this take? How did I calculate this number? It's this plus this plus this, right? So this number, that was easy. This number is this number. This number is this number plus this number, right? You have to add the previous, right? So what's that running time? That's going to be k squared. K is not constant. K is going to be a big number, right? Because I go, for this one, it takes me time k, right? So that's k squared. Does that make sense? Can you do it better than k squared? Yeah, in fact, it's easier than that. This, what's 17, right? This is the number summed up to here, right? Oh, this is the number summed up to there, and then we just add that on. This plus this is going to give it to us. Anyway, you look at it. So we can do it. We can do it in k time. Everybody with us here? It's just this number is the sum of these, and this number is the sum of those. So to get the sum of those, you add this number plus this number. Anyway, so this is where we did that. We counted. And now we have all of this stuff. And what do you think what's the meaning of 5? 5 tells me that there are 5 numbers smaller than 1. Right? So where does the first, what does this 5 tell us? The first 1 is going to go here. Right? Because they're 5 0, the 5 zeros are going to go here, and the first 1's going to go there. Right? So that's what I'm saying is the first 0 goes here. The first 5 is going to go there. The first 2 is going to go there. Does that make sense? Because it's the number that go before it. So that's great. What we're going to do is we're just going to go through the numbers and put them where they belong. All right? We get a 1. Where does it go? Goes in there. Right? Good. We get a 0. Where does it go? It goes there. Excellent. We get a 0. Where does it go? Why? But you didn't remember it. Right? What do we have? Everybody see? That's still there. We want to increment it. Right? So that was no good. Right? So instead, we're going to get a new loop invariant. The loop invariant says these values are the location or where the next time you see that value, where is it going to go? Right? So let's start over. We get a 1. It goes there. Where does the next 1 go? 6. So we change that to a 6, right? And then we get a 0, and the next one goes to 1, right? Does that make sense? And so we get a 0, we move, we get a 1, we move, we get a 3, and we move, right? We keep going. Everybody follow this algorithm? And it's all very exciting. You can see one gets so much joy out of making PowerPoint slides. All right, everybody got the algorithm? Yeah? So, I think we kind of actually did this once. Suppose I have a bunch of numbers, and I want to know the sum up to here, I'm going to write here. And the sum up to here, I'm going to write here. Right? So for this, if I added this, and then for this, I added this, and for this, I added this, then that's going to be k squared. But if for this one, I know here's the sum up to there, so for this guy, I just have to take this sum plus this sum. It makes it faster. Right? Anyway, so the point is, what's the running time in this algorithm? And we're going to say it's a linear running time. Right? And we're going to do some... I used to spend a lot of time analyzing the running time of this, and people got confused, and we're not going to spend that much time doing it now. All right? But we're going to chat about what it means to have a linear time running time. Because I was never taught this as an undergrad. What I was taught was a lower bound proving that you can't sort faster than in log n time. Right? So now I'm told that there's a linear time running time algorithm. And what do? I panic. I think, how can there be a linear time running time when you can prove you can't sort in faster than in log n time? And so that's what we're going to discuss now. So here's the bottom line. It's linear in what? Right? So when I say you can sort in n log n time, what that means is n is the number of numbers that you have, and each operation is you do comparison based. You have two numbers and you compare them. And how many times you have to compare two numbers until they're sorted, you have to compare n log n times. Right? But here, we have a different thing. It's the number of bits. So we have capital N numbers, right? And suppose each number, I haven't quite told you the radix counting sort algorithm. So let's do that now. Here, we got capital N numbers, and each number is L bits long, right? And we want to sort them. And the sorting time is going to be linear, not in the number of numbers. It's going to be linear in n times L, which is the total number of bits. Does that make sense? So its running time will be n log n in terms of the number of numbers. But in terms of the number of bits, the running time is going to be n times L. And the number of bits is n times L. So the running time is linear in the number of bits of the input. Does that make sense? All right. So we have capital N numbers, right? And so if we were to do merge sort, then every operation we would do comparisons, and you'd have to do n log n comparisons, right? This is on later slides. I'm actually getting ahead of myself, right? But what's the size of this input? It's n times L bits, right? Because we have each number is L bits, and we have n numbers. So the total number of bits is n log n. Right? And so now what's our running time going to be? It's going to be order n log n. So we'll review that in a minute, but let's go what the algorithm is. All right? The algorithm is we're going to choose some value k. All right? And later we're going to set k to be n. But that's when we're optimizing it. And what we're going to do is we're going to break the bits, these L bits, into blocks of size log k. All right? And so how many blocks do we have? We have D equals L divided by log n blocks. Right? We break it into blocks. Now, each block, right? Let's look at a block here. It has log k bits. Yeah? Log k? Log k is a parameter, and what I told you in the previous slide is that k is going to later be set to n. But right now it's a parameter. All right? We have some number k, and we break the blocks into size log k. All right? And now this number is log k bits. So how many different values can it have? Right? Well, there are 2 to the log n different values. There are k different values. Right? This guy here is a number between 0 and k minus 1. Right? Does that make sense? So for example, if I have 3 bits, the biggest as I can be is this. 2 to the 3 is 8. And what's this number here? This number is 7. Right? So they're between, and my smallest number is 0. Right? So they're between 0 and k minus 1. In this case, they're between 0 and 7. Does that make sense? Yeah, am I losing you? All right. So now what we're going to do is we're going to do, remember it's radix sort. We're going to sort these guys, right? And how are we going to sort these guys? We're going to use counting sort, right? We're going to sort these based on counting sort, and all this data is going to go with us. And then we're going to sort those using counting sort, and then we're going to sort those using counting sort, right? Does that make sense? And I made this up when I was writing the book. It's not, let's not get into it. And so the running time, we're not going to do the math on the running time, but the bottom line, if you go through all the math, is that the total number running time is n times L, right? Which is linear in the number of bits. So if little n is the total number of bits, then the running time is linear in the number of bits. People kind of follow that? And just to compare it to merge sort or quick sort, right? Here the running time is n log n, right? Here it's n times L. Well, what's L? Well, how many bits do you need to represent your numbers? If all your numbers are distinct, if you're not this guy where he's having everybody's name be the same, right? If everybody's name's distinct, then everybody has to have at least log n bits in their name. And so L is at least log n. So really this running time is the same. Don't worry about the details there. It's just that's... Everybody kind of get enough out of this that they want? All right. So here, later,